All right, our forces chapter was probably our biggest chapter, but we can, quickly remind ourselves of what was going on here. Okay, so let's say I've got a block, okay, that I'm going to pull, and we can pull at an angle or we can pull it straight. So if I pull it straight here, we know we'll have friction going against it in this direction. Okay, so that's force of friction. I'll label that force Fr. And this, of course, is the force applied. So then we know we'll have force gravity downwards, force normal upwards. Those will be equal. And our net force will be force applied minus force friction. And that, of course, equals ma. Now, if we pull at an angle, okay, I call this one force applied y. We just have to remember that force normal now is going to equal the force of gravity, which again is mg. And remember, it can be plus or minus the force applied y. We subtract it if I'm pulling upwards. If I'm pulling downwards, we'll add. That's how we do that. And then to get your net force, it's going to be force applied times the cosine theta minus friction. Of course, that equals ma. And remember, your normal force is going to be used to find force friction, and force normal multiplied by mu is always equal to friction force. All right, I'm going to take a look at an incline. If we have an object that's rolling down an incline, of course, we're going to have a different situation, but of course, we still have force normal upwards, and then we'll have force friction going against it. And remember, the force of friction is going to be static friction. Okay, and then what we'll be pulling it down is force gravity x. And remember, that is mg sine theta. We'll be looking at this again when we talk about energy that's involved, because when it gets to the bottom, we'll have rotational kinetic energy and we'll have translational kinetic energy. Now, the net force in this case is going to be mg sine theta minus force friction. And remember, that's a static friction, so that's not as easily calculated. And we'll talk about that when we get to rotational dynamics. If we have something that's sliding down an incline, of course, same kind of idea. We have force gravity x pulling it down, which again is mg sine theta. We have normal force going upwards. Okay, we'll draw our triangles underneath. Okay, so this is our force normal. And of course, we have friction force going against it. So we'll leave that as force friction. And remember, our angle theta is here, which is the same as this. This is our force gravity here in the y direction. So that's mg cosine theta. This is our force gravity x. Okay, and that's going to be mg sine theta. Remember, they're backwards on an incline. So your net force for this is going to equal force gravity x minus force friction. And that, of course, equals ma. Our next example here, what about a parachute? A parachute, you have gravity downwards, of course, and then you'll have air resistance upwards. And our net force this time is going to be, if you want to call downwards negative again, I'll call that negative. So my force net this time is going to be mg, which is force of gravity, and that'll be negative, plus the force of air. Now remember, when air resistance force equals force gravity, terminal velocity will be reached. And if you recall, we did an experiment where we looked at x versus t. Okay, and then we initially had like a parabola, then it went straight. Okay, this is where it's at constant velocity, and that's where air resistance force equals force gravity. Our next example is the elevator. Okay, we have, of course, force gravity downwards and force normal upwards. Okay, and a person standing on a scale. Okay, the scale is going to read the force normal, the amount of force being pushed from the surface upwards. If we're traveling at constant velocity, the scale is going to read force gravity. So let's say this person weighs 140 pounds. If the elevator is at constant velocity, it'll be 140 pounds. If it's accelerating upwards, it's going to read the weight of the person plus the mass times acceleration. So, again, force net is going to equal, force normal minus force gravity. This is our equation. And force net equals ma. Okay, so if we're accelerating upwards, then I'll have a positive a here. When I take gravity to the other side, I'm going to take ma plus force gravity. If we're accelerating downwards, then I'll have a negative acceleration here. So when I take force gravity over to the other side, I'll be subtracting and force normal will be less. So again, if I'm accelerating upwards, the scale is going to read more. If I'm accelerating downwards, the scale will read less, and the difference will be the ma that's involved. All right, what about our systems of blocks that are accelerating? Let's say this is 5 kilograms, this one's 10, and this one's 20. Okay, and that looks to me like to be 35 kilograms at most. Let's say we have 70 Newton force that's being applied here. I will then take 70. I guess my applied force is equal to 35A. So in this case, there's no friction. So 70 equals 35A. The acceleration then is equal to 2 meters per second squared. And I'm making it 2 for obvious. So if I want to find the tension force here, this cable has to accelerate the 5 kilograms at 2 meters per second, so that'd be 10 newtons. This one has to accelerate 15 kilograms, so that would be 30 newtons, because this one has to accelerate 2 at the same acceleration. So this would be 2 times 15 to get the forces between them. Okay, now what if I have a force pushing in this direction? They're the same blocks, and I have 70 newtons of force. Okay, so I'm pushing in this direction. Okay, I'm going to have the same acceleration of 2 meters per second. But what's the contact forces between these two boxes equal to? Well, this box has to push 15 kilograms at 2 meters per second. So the contact forces there is going to be 30, 15 times 2. And then what about the contact forces between these two boxes? Well, this box only has to push 5 kilograms at 2 meters per second. So that would be 10 newtons of force. Okay, and we're doing pretty well here. What about one last thing for us to think about for forces? What about an accelerometer? Okay, so let's say an object is accelerating and you have this in your hand. Okay, and it looks to me like our object then is going to be accelerating in this direction here. Okay, and then we're going to make an angle like this to the vertical. Here's angle theta. This is a very common system. So we have force gravity going downwards like this, and that's mg. Okay, and then we have force tension in the y direction going this way. And this, of course, is our force tension going in this direction here. Okay, our angle theta is also here. So this force tension y equals force tension, and that's multiplied by the cosine of theta. And this, of course, is just equal to mg. Well, these two equal each other. So that means force tension cosine theta does equal mg. Therefore, force tension is equal to mg divided by cosine theta. Okay, well, the force going in this direction is force tension x, and that's the opposite side of this. So force tension x is going to be equal to force tension times the sine of theta. And force tension X is what's causing this ball to accelerate, so that equals ma. Okay, now I'm going to fill in for force tension mg over cosine theta, and that goes there. So I've got ma is equal to mg divided by cosine theta. Okay, and I'm just going to multiply that times the sine of theta. I've substituted mg over cosine theta for force tension, but if I want force tension X, I'm going to take the force tension times sine of theta, and that's what I have. And if we look at this, the two m's will cross off, and sine theta over cosine theta is going to equal tangent. So the acceleration of our accelerometer is just g tan theta. And this is a common system that we see. So we have an object that's moving this way, and this accelerometer is going to swing backwards. It's just a pendulum bulb. Okay, and based on the angle theta, you can figure out its acceleration.